Welcome to the Radiation Safety and Computer Tomography Virtual Symposium. My name is Tony Seibert from the University of California Davis Medical Center. I am also a co-investigator of the University of California Dose Optimization and Standardization Endeavor. It is a pleasure to present this talk on incorporating dose monitoring software into RIS and PACS, current challenges and opportunities. As a disclosure, as part of the UC Dose Consortium, UC Davis uses Radiometrics exposure software and dose reporting capabilities. Why incorporate dose monitoring software? CT overdose events that were big news in 2008 through 2010 garnered the attention of legislators. This resulted in the implementation of SB 1237 and a law signed in the state of California requiring dose metrics be placed in the interpretive report. Efforts in other states are underway to get their own legislation invoked. It is the right thing to do for patients and their safety. In addition, dose reporting and tracking provides a mechanism to compare practices and develop low-dose protocols and techniques. There are several challenges that an institution must face to automate dose reporting. While from the surface it seems that radiation dose metrics can easily be extracted from the CT scan, this has been found not to be the case. Another issue is the myriad ways that a given exam is named and the need for a standard lexicon to appropriately sort the study types and their doses. Inserting dose metrics into the interpretive report is also a challenge, since the radiology information systems in common use have inflexible database structures. In addition, understanding the informatics infrastructure and working with IT personnel can also be very daunting, as they often see things from a different perspective. There are also many opportunities to take advantage of, some of which are listed here. Identifying high doses and outlier protocols, improving the delivery of patient care and safety, maximizing the benefits while reducing the risk of ionizing radiation, providing a feedback mechanism to lower dose, conforming to state law dose reporting requirements, meeting or surpassing community standards, and marketing low-dose capabilities and services at your institution. Dose reporting for CT begins with an understanding of what the dose metrics are and where they come from. On older legacy scanners, a dose report image is available with information encoded in a grayscale image, as shown on the lower left. Recent introduction of the radiation dose structured report provides a concatenation of relevant CT acquisition parameters that are useful in a structured format, in addition to the CT-DI-vol and DLP metrics. Over the past several years, there have been efforts to capture this data with open source and commercial software vendors. Radiance and PixelMed publishing software are examples of open source tools. In the state of California, legislation was crafted in response to many radiation overdoses and signed into law in late 2010, requiring the posting of dose metrics in the Radiologist report by July 1, 2012. UC Davis started a joint radiology and IT effort to create an automated dose report. A team consisting of IT personnel, PACS administrators, and medical physicists was established to develop a mechanism to automate the recording of the dose metric data in the Radiologist report. The initial UC Davis goals were to provide an automated dose report solution by July 1, 2012, to do the minimal data transfer of two values, an average CT-DI-vol and summed DLP, to meet the loosely interpreted requirements of the law, and to incorporate the values in the Radiologist report. The recently implemented RDSR DICOM module was not without challenges because of a new DICOM unique identifier and the lack of software to interpret the contents. In fact, when we initially sent the RDSR data to the PACS, it conflicted with our hanging protocols and disrupted radiologist workflow, so we stopped that feed. Several months of effort were required to determine how to get the dose data and ultimately validate the values. An existing DICOM HL7 interface engine was used to accept the RDSR data and convert the extracted and manipulated data to HL7, and then to send the content to a template in the speech recognition software. This is a diagram of the contributors and the progress made during the implementation of automated reporting. From the left are the identified CT modalities that produced an RDSR. Each scanner was programmed to send its RDSR data to the DICOM HL7 interface engine. Data extraction of the CTDI vol and DLP was performed and two numbers were generated. Dose data was then sent and incorporated into a defined speech recognition template. And then the finalized report was sent to the Radiology Information System and the EMR. This effort required about 1 year of study, validation, and implementation time. Transfer of dose information was achieved by January 11, 2012, with data transferred all the way to the EMR, as shown in the screenshot example above. However, only two values were sent, an average CTDI vol and summed DLP. While loosely meeting the intent of the law, averaging CTDI vol and summing DLP is inappropriate in most situations where combination studies are performed, such as the chest, abdomen, pelvis exam. Also, no explanatory text was offered in the report. And then a collaboration of the 5 UC medical centers funded by the University Office of the President, with Rebecca Smith-Bindman from UCSF as the principal investigator and representative investigators from San Diego, Irvine, Los Angeles, San Francisco, and Davis. Early consortium goals included recommendations for implementation of dose calculation tracking and reporting software, developing recommendations for compliance to SB 1237, and development of educational activities for optimizing CT examinations. In May 2012, the UC Dose Consortium defined recommendations for compliance to the state law in a letter transmitted to a wide audience in the state of California. This is an example of the cover letter. The UC Dose recommendations for the first part of the SB 1237 legislation, Section 115111 of the California Health and Safety Code for Public Health, is covered in this presentation. As stated in the letter, 1. Electronically send the scanner's dose report to the PACS. 2. Report CTDI vol and DLP for each series in the radiology report, and include the anatomic area imaged and the reference phantom size, or attach the protocol page to the radiology report, which is a reference to a paper as opposed to an electronic report. Continued details include: do not add the CTDI vol and DLP from different series, as adding them can be misleading. Moreover, reporting series values separately is unambiguous and recommended. Include explanatory text. The document provides an example of some possible contents as indicated here. More will be said about its length later in this presentation. Based on the active participation with the UC Dose guidelines, UC Davis stopped further development of its in-house solution. The capabilities of the radiation dose software vendor were used to automate dose extraction and include series-by-series values in the interpretive report. A step-by-step explanation of bulleted items is listed in this slide, undertaken to get the dose data from the scanner to the interpretive report. An interface diagram shows the flow of data directly from each scanner, indicated by the blue circle, to the dose calculation engine software, the red circle, as designated by the long dashed blue line. The dose software extracts the data and returns a message back to the DICOM interface engine as designated by the short dashed blue line. The interface engine then, in turn, sends the data via HL7 to the speech recognition engine, blue-orange dashed line, incorporating the data into the CT dose template field in the dictation report. This interface engine also orchestrates data flow for many other devices in the enterprise. Dose metric information becomes part of the completed interpretive report sent to the RIS from the speech recognition software, red dashed line, shown in the lower right area. Shown here is a multiple series exam with dose metric data nicely formatted in a table, series by series, using web services calls. Also note the fairly extensive explanation of the dose information below the dose data. Unfortunately, tabular formatting is not maintained with HL7 messaging and is lost when transferred to the RIS. resulting in a jumble of data in the RIS report. Implementation considerations include the following. The radiologist speech template must be modified to accept radiation dose data. Dose extraction and delivery requires a minimum of on the order of 10 minutes or longer, sometimes longer than the radiologist is willing to wait, particularly in life-critical situations such as trauma exams. CT exam spitting of combination exams is a huge challenge on certain vendor scanners, particularly in a busy emergency trauma situation, resulting in accession numbers with the same dose report and manual splitting that causes further delays in sending dose values. HL7 does not do tabular formatting of the dose data, making legible reports a challenge. Radiologists are also requesting minimal content so that the dose report isn't longer than the rest of the interpretive report. So, to shorten the report, a brief dose report format was implemented with series number, the body part, phantom diameter, CTDI vol, and DLP metrics and units listed, compatible with minimal formatting of HL7. Also, the descriptive information was shortened to see information on the Radiology website for further information. On the left, in the highlighted area, is an example of a single series exam dose report, and on the right, a multiple series exam dose report, demonstrating series by series data details on each line. Here is a screen capture of the dose information posted on the Radiology website. It is certainly useful for a medical physicist, but recently some of our radiologists have provided feedback by pointing out that the information is too technical. Updating the website to make the explanation of radiation dose and patient-specific criteria more understandable is a primary short-term goal to be undertaken. It's now been about 10 months since the law went into effect. We have performed 3 audits to date to see how we are progressing. Our audits indicate a steady improvement in compliance from 83.4% of all studies with correct dose reports in late September 2012 to 91.5% compliance on a single-day audit on October 9, 2012, and over 95% compliance on a single-day audit on November 29, 2012. Findings of the investigation reveal that, in many cases, a lack of template setup is a major cause of not having reports. Reports are late or are missing, and the radiologist fails to populate the dose info. Many studies, such as reconstructions, do not result in patient dose. This can be confusing, and radiologists are rightly concerned about indicating dose when no dose was actually given. Currently, we are making steady progress by adjusting dose software and hardware to become more efficient, such as increasing the memory size for the dose software program and database, and urging CT vendors to provide more effective ways to split exams with corresponding dose metrics. Dose information is being used as feedback to identify outliers and correct protocols when needed. Dose data is being sent to our local dose registry as well as the ACR dose index registry using the de-identification and forwarding capabilities of our dose tracking software. We are improving our website to be more useful to radiologists, referring physicians, and the public for understanding radiation dose metrics. So, in summary, we initially realized the difficulty in incorporating dose monitoring software in RIS and PACS, but recent entry of qualified dose reporting vendors into this informatics space has mitigated many of the problems. Many opportunities exist to improve patient care and safety, chiefly through feedback of mining and evaluating the radiation dose data. We are expanding the reach of dose monitoring to other modalities beyond CT, including interventional radiology, vascular and cardiac imaging, fluoroscopy and radiography, to get the full dose picture of patients in the medical imaging environment. Certainly, there's lots more to do to improve patient safety. Thank you very much for your attention in attending this seminar.